All right, people. So, welcome to your third lecture. In this lecture, what we'll be doing is we'll be trying to solve the fundamental problem of linear algebra. The fundamental problem of linear algebra is to solve a system of n linear equations with n unknowns, as in the number of equations equals the number of unknowns. Now, what do I mean by linear equation? I mean equations that have terms that are linear in the variables. As in, you don't have any quadratic terms, you don't have any cross terms, you don't have any terms like x squared or y squared or xy. Right, now consider the following simultaneous equations as in equation 1. Two variables, x and y, two variables, and two equations, right? Now, you know from your elementary high school algebra that this is enough information to solve these equations. Alternatively, look at the second set of equations, equation 2. You have three variables, x, y, and z, and three equations. Now, again, there's enough information to solve these equations. Now, why did I choose equations in 2 and 3 dimensions? Again, it's because it's easy to draw a geometrical picture for equations in 2 and 3 dimensions. It's easy to draw a plane in 3 dimensions or a line in 2 dimensions, or it's easy to draw a vector in 2 dimensions or 3 dimensions. However, it's hard to draw a hyperplane in over 3 dimensions. It's hard to draw a plane in 4 dimensions, and so on and so forth. Now, how do we picture these equations? Now, there are two ways we can picture them geometrically. One is the row picture, and the other is the column picture. Now, in the row picture, what we do is we take each equation, each row of the set of equations, right? And we consider what that equation looks like geometrically. So, for example, equation 3, right? 2x minus y equals 0. It's in red for a reason, and you'll see what the reason is. And negative x plus 2y equals 3. Now, you know by inspecting, you know through methods that you learned in high school, that the solution to this equation is x equals 1 and y equals 2. But how do we look at this geometrically? Using the row picture. So the red equation corresponds, the red equation here, to x minus y equals 0 in equation 3 corresponds, I'm sorry, this is taking some time to spell, corresponds to the red line in this diagram, right? And the blue equation, negative x plus twice y equals 3, corresponds to the blue line in this diagram. And notice at this point here, 1, 2, is the intersection of these two lines. And 1, 2 is the solution to our set of simultaneous equations. So that's one way to picture it geometrically. Similarly, if you consider the set of three equations, okay, so twice x plus 4y minus twice z corresponds to, corresponds to the blue plane in this diagram. Now, unfortunately, that plane is hidden away by the other two planes, by the red plane and the green plane. But if you plot these functions in Python or in Mathematica, or if you do this manually, you'll get the idea. Of course, the equation 4x plus 9y minus 3z equals 8 corresponds to the red plane, and the equation negative twice x minus twice y plus 7z equals 10 corresponds to the green plane. Now, all three planes have a common point of intersection, negative 1, 2, 2. So that these three planes intersect at x equals negative 1, y equals 2, z equals 2. Now, you plug this set of solutions into all three equations, this satisfies all three equations. So this is the unique solution to this set of equations. Right? So we can think of the solution to three simultaneous equations in three variables as the intersection point of three planes. For two simultaneous equations in two variables, we think of the solution as the intersection point of two separate lines. Now, what happens if these lines, they do not intersect, as in they're parallel? Well, you'll work on that case in the assignment. Now, this is not the only, the row picture is not the only way you can look at simultaneous equations. Notice that if you define the vector u as 2, -1, right, the column vector, the vector v as 1, 2, and the vector a as 0, 3, as in the highlighted vectors, you may write the first equation, as in this one, you may write this equation as 2u as xu plus yv equals a. Check it for yourself. Given the definitions of u and v, we may write that equation as xu plus yv equals a. So then the question becomes, right? The question then becomes, what linear combination of u and v becomes a? That is to say, if I have xu plus yv equals a, what are the values of x and y that are going to give me the vector a? We know beforehand that x and y are equal to 1 and 2. But notice how this works out in this diagram. Remember vector addition, right? We remember the law of triangle addition from the first lecture. So the vector u is in red, u. The vector v is in blue. So u plus 2 copies of v, u plus twice v, gives me a. This is how we look at it diagrammatically. Okay, so the vector u is in red, the vector v is in blue, and I make another copy of v. So u plus twice v equals a. So 1u, which is x, plus twice v, 2 because y equals 2, gives you a. This is the column picture. Similarly, we can use the column picture for equation 2, right? So in equation 2, remember you have 3 variables and 3 equations. So our columns are going to be 2, 4, minus 2, 4, 9, minus 3, and minus 2, minus 3, 7. That's exactly what we have here. 2, 4, minus 2, 4, 9, minus 3, minus 2, minus 3, 7. So the question is, what linear combination of these guys is going to give you 2, 8, 10? Because 2, 8, 10 is what you have on the right hand side. Now, of course, this is left to you as an exercise. You know what the values of x, y, and z are going to be. Just plug them in and represent the system of equations on a 3-dimensional diagram. So that's exactly what I want you to do in this exercise. Remember, exercises are important. You have to do them. They're not graded, but they're important. Okay, so now we come to the second part. When we look at the matrix form of the equations, right? So any set of simultaneous equations, right? If you have n simultaneous equations in m variables, now since we cannot call our variables x, y, and z anymore, we'll run out of variables, so we'll call them x1, x2, all the way to xm, right? So if you have n simultaneous equations, m n simultaneous equations in m variables, we can write them in general as c11x1 plus c12x2 plus dot 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 c1xm equals d1, c21x1 plus c22x2 dot 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 c twice m equals xm. So these dots, for example, in the second row, they represent c23x3 plus c24x4 all the way to c2mxm. Of course, going all the way down, cn1, cn2, cn1x1 plus cn2x2 all the way to cnmxm equals dn. Now, notice that, okay, so the c's, they are known as the coefficients in the equation, right? They're known as coefficients. Now, notice that I can represent this set of equations as an equation 5 in matrix form, Cx equals D, where C is an n by m matrix with real number entries, of course, because I'll offer in this course, everything is going to be real number. I'm not going to bother. I'm not going to burden you with complex numbers. You can extend whatever theories you've learned in this course to complex numbers later on. This is an n by m matrix with real number entries. X is an m by 1 vector, and D is a constant n by 1 vector with real entries. Okay, so if C is given by, so notice I can do this. So I want you to work this out. If I multiply this C by this X, notice the C is an n by m matrix. So n rows, m columns, and X is a vector that has m rows and 1 column. So I can multiply Cx. And when I multiply Cx, I'm going to get a vector that is n rows and 1 column, which is my D. So I can represent this entire set of simultaneous equations in this compact matrix form. Right? Now, what we'll do at first is that we will examine the case in which C is a square matrix. What does that mean? If C is an n by n square matrix, this means that this set of equations has n equations and n variables. We have the same number of equations as variables. So we have enough information to solve the set of equations. Now, if that is indeed the case, if Cx equals D, then I can multiply both sides by C inverse, right? Left hand side and the right hand side. Now, by the associative property of matrix multiplication, I can associate C inverse and C. I could do C inverse C first, and then before I multiply that by X. So this equals C inverse D. But C inverse C is just identity matrix. X equals C inverse D. But if you, of course, this is the n by n identity. X is an n by 1 vector. C inverse C equals I. That gives you the n by n identity matrix. But Ix is just equal to X. And so X equals C inverse D. So X is, of course, the solution set, the set of variables, right? So this equals C inverse D. Remember, C inverse is a matrix with the C is the coefficient matrix. So if C is invertible, I can write this, and of course D is the is what you have on the right hand side, right, is a set of numbers on the right hand side, d1 all the way to dn. So C inverse D gives you the solution set to the equations. Now, let's take a concrete example. Let's go back to equation 1. So remember what equation 1 was? This was equation 1. 2x minus y equals 0. 2x minus y equals 0. And minus x plus 2y equals 3. Now, since I've taught you matrix multiplication, you should be able to write equation 1 as Cx equals D, where C equals this matrix, right? 2 minus 1 minus 1, 2. These are the coefficients, right? So this is the coefficient of x in the first equation. This is the coefficient of y in the first equation. This is minus 1 is the coefficient of x in the second equation. And 2 is the coefficient of y in the second equation. So, of course, x equals xy. These are the variables that you have. And d is what you have on the right-hand side, 0, 3. Now, let's go through this procedure to solve the equation. Now, you have Cx equals D, right? Now, x is, of course, given by C inverse D. Now, what is C inverse? Now, from this first assignment, you know how to calculate the inverse of a 2 by 2 matrix. I haven't taught this to you for higher order matrices, but you know this for a 2 by 2 matrix. So plug that into this formula, and you get C inverse equals this guy. 1 over 3 times 2, 1, 1, 2. Thus, x, which is equal to xy, equals 1 over 3 times 2, 1, 1, 2, times d, which is 0, 3, which gives you 1, 2, which is 1, 2, which gives you 1, 2. So therefore, the first row, which is x, equals 1, and the second row, y, which is equal to 2. Now, similarly, for the three-dimensional equation, as in the three-equation system, you could write the matrix C as this. You should be able to, these are the coefficient matrices. So this is the coefficient of x in the first equation, coefficient of y in the first equation. 4 is the coefficient of y in the first equation, minus 2 is the coefficient of z in the first equation. So 4 is the coefficient of x in the second equation, 9 the coefficient of y in the second equation, and minus 3 the coefficient of z in the second equation, and so on and so forth. And your vector x is, of course, x, y, and z. I could have, more typically, what you do is you write these as x1, x2, and x3. And on the right-hand side, you have d, which is 2, 8, 10. Now, you don't know how, in principle, I haven't taught you how to invert a 3 by 3 matrix. But what I'm going to do is I'm going to do this I'm going to plug this 3 by 3 matrix into a computer and write the inverse as the inverse of the coefficient matrix as 1 over 4, 27, negative 11, 3. So this is the inverse of this guy. This is my claim. So now, using the definition of the matrix inverse, right? Here's what you can do. You can, the exercise asks you to verify, right? To verify that this is indeed the inverse of the coefficient matrix, this guy. This is indeed the case. How would you verify it? You would just multiply the coefficient matrix by this guy and see if you get the identity matrix. And of course, using equation 2, right? And of course, using this solution, this inverse, you solve equation 2, which is of course this. Which is of course this set of equations in 3 dimensions. This set of equations in 3 dimensions. All right, great. Uh, Now, of course, in the column picture, this is very important, and you're going to need this fact for your assignment, right? That assignment or the exam. Notice that in the column picture, the column vectors are the columns of the coefficient matrix. All right. So, for example, in the coefficient matrix for equation one, what was it? 2 minus 1, right? 2 minus 1 and minus 2, minus 1, 2, right? These are the columns in the coefficient matrix of equation 1, as in the 2 by 2 simultaneous equations. The, the two simultaneous equations with two variables. Right, now notice that these are exactly the vectors that we are using, right? 2 minus 1 and minus 1, 2. Actually, v, I think yeah, v should be minus 1, 2. There's a slight typo here. Here, v should be minus 1, 2. I'll fix the typo in the updated version. V should be equal to minus 1, 2, not 1, 2, because notice that the blue vector is pointing in this direction, in the negative x direction. So the x component must be negative, right? So notice in the column picture, or for example, for the 3 by 3 matrix, right? What are the vectors in the column picture? 2, 4, minus 2, 4, 9, minus 3, and minus 2, 3, minus 7. Let's look at the coefficient matrix. Okay, so these are the vectors in the column picture, right? 2, 4, minus 2, 4, 9, minus 3, and minus 2, minus 3, 7. Now let's look at the coefficient matrix. 2, 4, minus coefficient matrix is 2, 4, minus 2, 4, 9, minus 3, and 2, minus 3, 7. So the columns in the coefficient matrix are the same as the columns in the column picture, the column vectors in the column picture, right? So if the columns of the coefficient matrix, they span Rn, which is n-dimensional vector space, real vector space. If that is indeed the case, then we can claim that then we may claim that there are solutions to Cx equals D, where C is an n by n coefficient matrix, X is an n by 1 column vector, and D is an n by 1 column vector. Now, if we have a system of equations, Cx equals 0, 0 bolded, 0 is of course the 0 vector where all the entries are 0. If the only solution to this is x1 equals x2 all the way to xn equals 0, then this equation is said to have only the trivial solution. Okay, so 0 is the n by 1 0 vector where all the entries are 0. Now, my claim is, so I'm going to claim, okay, let's call this theorem 3.1. This is the third chapter, and this is the first theorem in the third chapter. If C is an invertible n by n coefficient matrix, then the set of equations Cx equals 0 has only the trivial solution. Okay, meaning if C is the so the solutions to this equation are x1 equals 0, x3 equals 0, all the way to xn equals 0. Now, let's prove this. If cx equals 0, then of course I can multiply both sides by c inverse because c is invertible. Remember, we have an inverse for c. Equal, meaning c is non-singular. Because if c were singular, there would have been no way for me to multiply to form this inverse. So I can associate c inverse and c together with associativity property. Now c inverse times any matrix times the zero vector is going to give you the zero vector, right? Because all the entries of the zero vector are 0. So c inverse c is I. So ix equals 0. So I is the identity matrix with the correct dimension. So this gives you x1 all the way to xn equal to 0 vector. So that gives you the trivial solution only. Okay, so we're done with our proof. This is exactly what we were looking for. Now, of course, we'll discover soon that this is actually an equivalence relation, meaning if cx equals 0 has only the trivial solution, then c has to be invertible. Okay, so this goes both ways. This is going to become an if and only if relation. So C is an invertible n by n matrix if Cx equals 0, IFF Cx equals 0 has only the trivial solution. But we'll come to that. We'll come back to this later. Okay, now we look at the process of Gaussian elimination. What is Gaussian elimination? Right. So consider equation 1, right? Twice x minus y equals 0, and remember equation 1? There's twice x minus y equals 0 and negative x plus twice y equals 3. Right. So let's say you were asked to solve equation 1. Right. So how would you go about it? You would multiply, of course, the second equation by 2 and add that to the first equation, right? Because there's a negative 1 here. You add that. So multiplying it by 2 makes it negative 2. Add that to the first equation. Of course, that gives you 0x, which is 0 basically. So then you would divide the second equation by 4 and the first by 2. And you would end up with y equals 3 over 2 and x equals, and you would substitute that value of y in the first equation, right? And you would get the value of x. Now notice that you were performing operations on the rows of the equations. These are on the rows or the individual equations. These operations, add the second, multiply an equation by 4, or add 2 equations. These are called elementary row operations, right? Now, what elementary row operations constitute, I will define later, right? But first, what we're going to do is we're going to get rid of all the. We're going to use better notation. We're going to get rid of we're not going to get rid of the variables. We're just going to hide them. We're going to suppress them, right? Because we know that they're there, right? So what we need is the coefficient matrix, right? And we need the thing that's on the right, the right hand sides of the simultaneous equations, right? So let's go back to equation 5. Okay, so remember that this is our coefficient matrix, right? C is our coefficient matrix, and D is what's on the right hand side of the set of simultaneous equations. So what we're going to do is going to write the coefficient matrix and separate it from the right hand side of the equations, and with this entire matrix, right, in equation 7 is known as the augmented matrix. By augmented, we mean that it has been made bigger. Okay, so this is augmented matrix form. Now, notice that there's a barrier here. This barrier, mathematically, it means nothing, right? I mean, we could have done without this barrier, right? And some people, however, what we need to do is we need to separate the coefficient matrix from the right hand side of the equation, right? So there are other ways to do this. You could make this bold. That's entirely up to you. So you don't worry about the presence of this barrier, right? It's not going to influence anything. It's not going to affect how you perform your elementary row operations. Okay, so let's go on. So what we're going to do is, the objective is to perform elementary row operations until the entire augmented matrix is either in row echelon form or in reduced row echelon form. Now, what does this mean? Okay, first of all, let's some notation, right? The ith row of the augmented matrix we will denote by R sub I. So now, what does it mean for it to be in row echelon form? So if you have a row, okay, so these are the criteria. If you have a row that consists entirely of zeros, right? So for example, if there's a row here, let's see, 0 0 0 0 0 0 all the way to the end, zeros, right? Then that row must be at the bottom, right? That row must be at the bottom. The leading coefficient, meaning the first non-zero coefficient of a non-zero row, is always strictly to the right of the leading coefficient in the row above it, right? So the 3 by 5 matrix, so this 3 by 5 matrix is in row echelon form. Why? First of all, there are no rows that are entirely zero here. What are the leading coefficients? In the first row, the leading coefficient is 1. In the second row, the leading coefficient is 2. In the third row, the leading coefficient is 1. Now notice the leading coefficient is always the first, and that's how it's defined, is always the first non-zero coefficient in each row. And now notice also that the leading coefficient in the second row is to the right of the leading coefficient in the first row, and the leading coefficient in the third row is to the right of the leading coefficient in the second row, and so on and so forth. Now these leading coefficients, they're also known as pivots, right? Okay, so this is a matrix in row echelon form. Now, in order to form a matrix in reduced row echelon form, that's going one step further. What has to happen is that first, of course, your matrix has to be in row echelon form, meaning it has to satisfy the first two conditions, meaning these have to be true, these guys have to be true, right? These 2 points have to be true. Furthermore, the leading coefficient in each non-zero row has to be equal to 1. So there's a 2 here, right? This leading coefficient is 2, or this pivot is 2. So this is not in reduced row echelon form. This is in row echelon form, but not in reduced row echelon form. Now, each column containing a leading 1, right, has zeros in all other entries, right? So for example, this column, right, that has a leading 1 has zeros underneath it. This column that has a leading 1 has a 0 above it and below it. This column that has a leading one has zeros above it, right? So 1 0 0, right? So this is in reduced row echelon form. Notice this guy, this matrix, right? This leading one has zeros below it, but this leading one does not have zeros above it. Okay, so given these conditions, this guy is in reduced row echelon form. Okay, so you'll have to be able to identify if a matrix is in row echelon form or in reduced row echelon form. Okay, so that's something you'll have to do. So here's what I'm saying is that please do not be put off by the fact that in augmented matrices there's a vertical line separating the last column from the rest of the matrix. Pretend that that line isn't there. We only draw it to separate the coefficient matrix from the right-hand side vector of a set of equations that is vector t. Okay, now what are the rules of the game, right? What are these elementary row operations that you are allowed to use? Okay, so the elementary row operations that you are allowed to use are as follows. You can multiply the ith row by a non-zero constant c, as in you can turn Ri into CRI. You can interchange two rows, as in you can take the ith row and put it in the jth row, and the jth row and put it in the ith row, right? That's allowed. And you can add a constant c times one row to the other, right? So you can turn Ri into Ri plus CRJ. Okay, so these are the things that are allowed. You're allowed to do these. So these are the elementary row operations. So now let's apply them to solve simultaneous equations. So remember equation 1. So if you remember equation 1, what we can do is we can solve the equation, right, using elementary row operations, right? We can so here what I've done is I've only done taken it to row echelon form. I haven't taken it down to reduced row echelon form. I'll add the reduced row echelon, add the steps to take it down to reduced row echelon form later. So what I've done here, okay, so this is the augmented matrix, right? So to the left of the vertical line, you have the coefficient matrix. The right of the vertical line, you have the right-hand side of the equation. Right now, of course, doing one step takes it to row echelon form, right? So R2 takes you to R2 plus half R1, and you're in row echelon form already, because the pivot point are 2 and 3 over 2, right? So R2 goes to R2 plus R1, right? So R2 is minus 1, 2. So if you add this to an R1, the second row is minus 1, 2, 3, right? So half R1 is 1 minus half and 0. So if you add R2 to half of R1, you get 0, 3 over 2, and 3, right? Because minus 1 plus half of 2 is 0. 2 minus half of 1 is 3 over 2, and 3 plus half of 0 is 3. So from here, we can actually solve the equation, right? So I haven't finished the reduced row echelon form, right? So there are a few steps left here, but what we can do here, from here, you can actually deduce that 3 over 2y equals 3, because remember, this is the coefficient matrix, and this is the coefficient of y. So 3 over 2y equals 3, which gives you y equals 2. and plug this into 2x minus y equals 0, meaning the first equation is 2x minus y equals 0, and you have x equals 1. So we'll look at the reduced row echelon form on this later. However, the next equation, okay, there's another thing that's important, is the row echelon form is not unique. However, the reduced row echelon form is. What do I mean by that? Notice that here we have the row echelon form, right? 2 minus 1, 0, 0, 3 over 2, 3. Now, if instead I had multiplied the second equation by 2, for example, right? I'd have gotten 0, 3, 6. Sorry, if I had multiplied the second row by 2, the same as saying the second equation, but since we're dealing with matrices, we'll call them rows. If I had multiplied the second row by 2, I'd have 0, 3, 6. And that would, of course, would still be in row echelon form, but that would not be unique. But then the row echelon form is not unique. However, the reduced row echelon form, it is unique. So what I mean by that is that I ask you and your friend to reduce a matrix to row echelon form. If the two of you get two separate answers, you still might have gotten the right answer, right? I mean, that's why it's not. That's what I mean by it's not unique. But if I ask you to reduce a matrix to reduced row echelon form, you know that it's you know that the two of you have to get the same answer. Okay, so let's look at the the three equations, right? So remember, this was a question matrix of equation 2, 2, 4 minus 2, 4, 9 minus 3, minus 2 minus 3, 7. So this is the question matrix, and of course on the right you had 2, 8, 10. So let's try some elementary row operations, one after the other. So how do we proceed? Of course, I want this to go all the way to reduced row echelon form, right? So I want as many zeros as I can. Okay, so okay, so I want I want to make this 0. I want to make these guys 0, and I want to make these guys 0. Okay, so my mission is to make these guys 0, 4 and minus, to make this guy 0, and to make this guy 0, and to make these guys 0, right? Okay, so let's see what happens. So let's see one way of making this guy 0, right? So this 4, I want this to be 0. So if I do R2 minus 2 R1, right? So this is 4 and this is 2. So 4 minus 2 times 2 is 0. And 9 minus 2 times 4 is 1. See, I've got 1 already here. And minus 3 times 2 times negative 2 is 1. And this becomes 4. Cool. So, and since I want this guy to be 0, so R3, I can make it R3 plus R1. So which gives me minus 2 plus 2, which is 0. Minus 3 plus 4, which is 1. 7 minus 2, which is 5. And 10 minus 2, 10, sorry. 10 plus 2, which is 12. Okay, so now R1 goes to R1 over 2, right? So remember, it was just 2, 4 minus 2, 2. So remember, the pivot points have to be 1. So this is why and this is the pivot point of the first row. So I divided by 2 to make this 1. So I get 1, 2 minus 1, 1, right? And okay, so now I want to make this guy 0. So I do R1 minus 2 R2. So R1 minus 2 R2. So notice that this is 1 minus 0, 1. right? So 2 minus 2, this is going to make it 0. Minus 1 minus 2 is going to make this 3 minus so 1 minus 8 is going to make this minus 7. So we've changed R1 to this. So now I want okay, so and then R3, so I want this guy to be 0, right, as well, because remember this column, this is remember, in columns containing pivot points, every other element has to be 0. So R3 becomes R3 minus R2, because 1 minus 1 is going to give me 0. So you get a 0 here. So 5 minus 1 is 4. 12 minus 4 is 8. Okay, so this is our matrix so far. Notice that it's already we've already achieved row echelon form, because the pivot points are to the right. The pivot point in R2 is to the right of the pivot point in R1, and the pivot point in R3 is to the right of the pivot point in R2. So then, of course, this pivot point has to be 1. So I divide this by 4, I get 0, 0, 1, 2. So now what I need to do is I need to make these guys 0, right? These guys, I need to make these guys 0. So of course, to make this minus 3 0, it's easy. You get the R1 plus R1 changes to R1 plus 3R3. So minus 3 plus 3 times 1 gives me 0 here. And of course, minus 7 plus 6 gives me minus 1 here. And I need to make this guy 0. So the best way to do it is changing R2 to R2 minus R3. So 1 and minus 1 cancel out to give me 0. And 4 minus 2 cancel out to give me 2. So this is in reduced row echelon form. So let me tell you something here. If a matrix C is invertible, then the reduced row echelon form, and if it is square and invertible, then the reduced row echelon form is going to be the identity matrix. Of course, from this reduced row echelon form, we can read out the solutions. X equals -1, y equals 2, and z equals 2. Right? If you switch the equation picture. Now, again, then why is this in reduced row echelon form? All the pivot. First of all, this is in row echelon form, right? There are no 0 rows, so I don't have to bother about them. But notice that the pivot point in the second row is to the right of the pivot point in the first row, and the pivot point in the third row is to the right of the pivot point in the second row. In fact, we already had row echelon form by this point, right? This is in row echelon form. Now, with columns that contain pivot points, all the other entries are 0, 0, 0. Okay, so from this, of course, we can read off the solutions of the equation in the equation picture, right? So now, I know you're going to be asking for more and more practice. So what I've included a link here. There are plenty of practice problems with answers here. Right? Click on the link, and this takes you to takes you to a nice practice worksheet. There are 25 problems here. You could do all 25 if you need to do them, and there are solutions included at the end, right? So you have to, all of these you have to take into reduced row echelon form, right? So yeah, so that's the end of the lecture. Thank you very much for listening, and please, of course, please ask me any questions should any arise. So I'll put everything up on YouTube and Vox by today. Thank you.